Okay. The last week we discussed about the 2020, I think 2021 paper. Today let's start with the 2020 past paper about the part B, question number past paper 2020, question number 5 in part B. Fine, let's start. So this is your question. So I'm going to draw the truth table for this one. So your A part is give the complete truth table for the given circuit diagram. Give me a minute, I'll show that. Let's see. They give the complete truth table for the given circuit diagram. So here A, B, C. So the second one, A plus B, here B plus C, this is C. So A plus B, B plus C, and C. And A plus B dot B plus C dot C. So this is your final answer, which means it's Z. You don't mention that all things. Simply you can mention this one. So here 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. So this is your basic input. I hope you know this one. And A plus B is equal to 0, 0, 1, 1, 1, 1, 1, 1. And B plus C is equal to 0, 1, 1, 1, 0, 1, 1, 1. So the Z answer is with the C altogether. And so 0, 0, 0 is equal to 0. 1 into 0 is equal to 1. Sorry, 0. 0 is equal to 0. So this is also 0. This is 1. This is 0. This is 1. This is 0. This is 1. So this is your final output. Okay. So, so the first question, A part, the answer is this. Second question, using a Karnaugh map, drive a simplified SOP expression for the output Z. Okay, the last time they have given that style, so either you can use this size A, B, C. Zero, 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 one, 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 zero. 0, 1. Okay, so this is one of the style. Even you can follow this A, B, C also. Okay, so the A means 0, so this is also possible. Why? Because there is no format, but the last time in 2021, they have given the formats, so that's why we have to follow that one. But at this point, you can even follow the ABC or this format also. So the both are correct. I'll just use this vertical, horizontal, and let's see. So here this is your final output. So no need to worry about this one. So the final output is 0, 0, 0. So altogether 0. Just they have mentioned using Karnaugh Maps, driver simplifies sum of product expression for the output Z. Okay. In this scenario, this so even you can mention only the ones only because this is a SOP format. This is SOP format. The POS is look like this. I showed it. So this is a POS, this is a SOP. So question number A, question number B. So here the one is the combination is 0, 1 and 1. So here 1. This one is correct. So the second one 1, 0, 1. So the A is 1, B is 0, C is 1. So here it's also fine. So A, B, C. A, B, C 1, 1, 1, 1. So this is your next item. So even I just fill this one because for this zeros, the all are zeros. And second one is A B 0 and 1 is 0. I'll just use this symbol. And 0, 1, 0. A is 0, B is 1, C is 0. A is 1, B is 0, C is 0. A is 1, B is 0, C is 0. A is 1, B is 0, C is 0. And A is 1, B is, so 1, 2, 3, 4. These also fine. So A is 1, B is 1, C is 0. So this is your POS output and this is your SOP output. Fine, let's do the SOP. So the group, you can make a group, two groups here. Number one, green color. Number two, the blue color. So group one, and this is your group two. Okay. So what is the green color thing? Test the group 0, A is equal to 0, say A bar, B and C. Second one, A, B and C. So this group A, B, C, and for this one A, B bar, C. So easily you can cut it off this one, and the BC is the answer plus A is general, so B cut AC. So this is your answer. BC equal AC. So the SOP BC plus AC. For the POS, let's group it. As you know, the rule number one of the rule is maximum. You can group the 2 to the power combination with the large as possible. So this is the one group and this is another group. Okay. So let's see. Group 1, and for this even I can write it down here. Group 2. So the first combination A, B, C. I hope you know this why this one is a ABC. Clear? Okay. So the second one A, B bar and C, and A bar, B bar and C, and the fourth one A bar, B and C. So this is your answer. So you can simply cut it off A and A, and for the B and for the B. So finally, the C is the answer. C plus, and the group 2, A, B and C. And second one, A, B bar, C bar. So C bar is cut dot A plus B. So here everything is plus now. Finally, C dot A plus B. Okay, so now you get the idea. So this is your SOP answer, and this is your POS answer. The final question is justification. Of the two expressions, SOP and the POS, you obtained in B and C above, which one is better to implement a more simplified logic circuit than the given logic circuit above? Explain your answer. Okay. So your justification, I just raise this. Okay, look at this. Your SOP is equal to BC plus AC. For the POS, is equal to C dot A plus B. So this is your answer. So in here, what you can do for the justification, simply you can find it out how many logic combinations, logic circuits, logic symbols, logic points are there. For an example, here look at this. The OR is there here, and here OR, and here AND. Altogether, you have to use the 3 logic circuits. Logic gates, sorry. So 3 logic gates, altogether 3 logic gates. Here, you have to use only the AND OR. So from here, by using this expression, even you can justify. Okay, what you can do, the SOP answer, the SOP expression has 3 logic gates. To the POS expression, POS Boolean expression has only 2. So therefore, the simplified version is POS. So therefore, simplified version is POS. Either you can use directly without any other logic circuit diagram. Even you can draw the logic circuit diagram, and even you can show it B, C, A. So the B is AND gate, A is AC, the OR. So how many? Number 1, number 2, number 3. But for the POS, the C is there. A plus B. You got it? So now you can say what? Here in the sub portions, we have to use 3 logic circuits, logic gates to make this circuit. But for the POS, you need only the 2. Therefore, this is a simplified logic circuit diagram. So therefore, we are preferring this one. So you can say it's
the most preferable. I think they are also asking about the preferred expressions of obtained one of the better implementation, simplified logic circuit. Yes, of course. The most better one is this one. What is the reason? Because here you have 3 logic gates, here only 2 logic gates. Okay. So let's move to the 2019 paper. Okay. The 2019 paper, the same part B, question number 1, which means altogether question number, when you compare with the part A, the part A ended up with the 4th and 5th is start with the number 1. So therefore, part B, question number 1. Okay. Is this clear? Any doubt? Please let me know. If you have any other issues, please let me know. I will explain it. Okay, even you can ask the questions during the class sessions and I'll explain it. Okay. Okay. Now let's start. The Boolean function known as the majority functions. Take n binary inputs. So you have a give the truth table for the 3 input majority function. So the truth table first A, B, and C. So simply you can 0, 1, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 0, 0, 1, 1, 1, 1. Okay, so this is your answer for the Z is the output. Okay, let's see what is the output. First, what they say is the Boolean function known as the majority function. There is a binary inputs and the output 1. Binary inputs and outputs 1. If a majority, at least half of the inputs are 1. So which means if there is a 2 combinations, the output is 1. There is a meaning. So that's why they say majority functions. So binary inputs and outputs 1. If a majority, at least half, which means the 3 is there, which means half means 1.5. There is no 1.5 combinations. So therefore, at least 2. If at least 2 combinations are there, the input combinations are there, so you can take it as a 1. At least means not only. So the at least means minimum 2 or the maximum 3 is also possible. So therefore, here this is directly you can say 1. And for this, here 1. For this, you can write it down the 1. And for this, 1. And the rest of the things, 0, we'll see. Otherwise, it output 0. Let us consider the case when n equal to 3, which so there is no any other statement. So directly you can say, if the 2 inputs are there, you can take it as a output, take it as a 1, and for your at least. So therefore, if it is a 3 inputs, you can take it as a 1. So this is your output. Otherwise, it outputs 0. So you can take it as 0. So 0, 0, 0, 0. So this is your output. Okay. Number 1. I'll repeat it again. The concept is majority functions. So the majority functions, the scenario is the criteria, the binary input and output 1. Okay, if a majority, at least half. So half means you can't take it as a 1. Only 1 input. So you at least you need a 2 inputs. If both are 1, your output is 1. Or more than that, at least 2. At least. So therefore, at least means 1, 1. And the third also, you can take it as a 1. So if that's why here, this is 1, at least 2. Here also at least 2. This is 1, only 1 is there. So at least 2. The rest of the things are zeros. Okay. So this is your output. And give the truth table. So this is your truth table. So simply you can get the full marks for the A. Question number 1. This is 2019 past paper. Part B, question number 1. And A part. So the B part says using KMap, Karnaugh Map, drive a simplified Boolean expression for the output Z in the 3 input majority function. So the when they are mentioned the Karnaugh Map without any other SOP or POS, typically we are using a SOP. Clear? So that's why in your syllabus they mention the rule number 1, not allowed 0, not allowed 0, which means the typically we are taking as a SOP, so sum of product. Okay, so therefore the sum of product is based on the ones. So let's start with the ones only for the Karnaugh Map. Let's show the Karnaugh Map. So here A, B is there, C is there. Zero, 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 one. Okay. Let's apply this ones. Here A is 0, B is 1, A is 0, B is 1, and C is 1. So this is 0. So the second one, A is 1, B is 0, and C is 1. This is also fine. So the third one, A, B, and C. And the final is this. Okay. Here we can rub this first combination, second combination, and the third combination. Okay. You have 3 combinations are there. So let's see. Group 1, group 2, group 3. So the first one, A, B, A bar, B, and C. So the second one, A, B, and C. So you can cut it off, the balance is B, C. For the group 2, A, B, and C. For this one, A, B bar, C. So B is AC. For the group 3, A, B, and C. So C bar, and A, B, and C. So therefore AB. So the final answer, BC plus AC plus AB. BC plus AC plus AB. Okay, this is your SOP answers. Okay. So it's a very simple term, so no need to worry about directly you can write it down. The 2019 is a really easy question. So even my unit exam is also follow the same structure. So even you can answer that one. Okay, but the final C is the little bit of a different, what is that? NAND gates. Now, construct a logic circuit for the 3 inputs majority function using a NAND gates only. Using Karnaugh Map, drive a simplified Boolean expression for the output Z in the 3 input majority functions. Okay. here they mentioned the construct a logic circuit for the 3-input majority function means this is a 3-input majority function. Okay, as they mentioned earlier, the Boolean expression function known as the majority functions takes n binary inputs and outputs. One, if a majority at least half of the inputs are 1, otherwise it inputs 0. Okay, for these majority functions, you can't get the expressions. Without the expression, you can't draw the what do you call logic circuit diagram. So therefore, we can use this BC, AC, AB is the answer. This is the logic expression. Fine. Let's draw the NEN diagram. I'm using it. I'll raise this one. Okay. Here the BC. So the BC means here simply first I'll just draw the simple version. B, C, A. So the first is BC and the AC and the AB. So even I can use like this, then it will be for me to draw the. Okay. So this is your what BC, AC, and AC. So this is BC. This is BA. This is BA. AB or BA. This is BC, and this is AC. AB, AC, BC. So now let's see how to draw this one. First of all, you know in our first step, the first session, we discussed about the universal gates. Okay. So now they have mentioned the NEND. Okay, NEND. So NEND means for this one, this is the NEND and are both same family. Therefore, we are using a linear NEND. So here, so AB, I just show the AB. I'm trying to use the same structure, then it will be easy. So the A, B, and C. First is BC, second is AC, third one is AB. So this is your typical circuit diagram. Now we are applying the for this one first B and C. So let's see for this B, A, B, C. For the and you know there is a NAND gates is the both same family. So this is equal to N, number one. So the second one, A is there, C is there. So let's see, A is there. So this is C, this is B. And for this A and C. So the same answer. And for this AB, Fine. Now we are going to use the this one. What do you call it? OR gate, implementing OR gate by using the NAND. So this is both are not same family. So what you have to do, you have to use the parallel pattern. So this is your first and second E. Now so this is your OR gate. So the second OR, okay. Is this clear? Any doubt, please let me know, I'll explain. So this is your diagram. NAND gate diagram. So this is a universal concept. Please go through the universal concept. If the both families are same, we are using a linear manner. If the both families are different, so we are using a parallel manner. So this is a fundamental concept. Okay. Any doubt, please let me know. So you can use the chat